Welcome back, Chem 201 Organickers. This part of the lecture is going to be about functional groups. I'm going to expand a little bit, sort of increase what's usually covered in Chapter 1. There's a separate PowerPoint presentation that I put together for this. So we're going to go over that, and again, that will be posted with this video on our Blackboard site. So let me share my screen and let's start looking into functional groups. Okay, so in organic chemistry, we are going to classify compounds into families based on structural features. The chemical behavior of those family members is often predictable based on their specific grouping of atoms. There are a few general families of organic compounds whose chemistry falls into simple patterns. And these structural features that allow classification of organic compounds into families are called functional groups. Functional groups are what we're going to study in this class. Every chapter is based on a different class of compounds, mainly according to what functional group the compound is classified into. We're going to see that a lot of the chemistries of a specific functional group are very similar. So a functional group is defined as an atom or group of atoms within a molecule that has a characteristic physical and chemical behavior. Each functional group is part of a larger molecule, and a molecule can have more than one class of functional groups present. In fact, many complicated natural products that are used as medicines can have a large number of functional groups that are present, which makes the synthesis of them, which is making them from small pieces that you can buy from a chemical warehouse supply group, pretty exciting and fun. That's what organic chemists, I'm a synthetic organic chemist, so I always enjoyed making these big molecules. A given functional group is going to tend to undergo the same reactions in every molecule that it contains because it's the chemistry. Every functional group that's an alcohol has an OH. Every functional group that's a carboxylic acid has a C double bonded O to an OH, right? So alcohols will have OH. Carboxylic acids will all have this. Ketones will have a functional group like this. Well, since this structural piece here is the functional group and is common to every molecule that has that, the same structural features, right, in these functional groups, whether this is attached to something, much different, the chemistry is the same. So the chemistry of an organic molecule is primarily determined by the functional group it contains. Simple compounds that have one alcohol, they're going to do what alcohols do. Very complicated structures that have an alcohol, that OH is going to do what alcohols do, right? So the chemistry is actually dictated by the functional group and not by the size or the complexity. So this is a chart that has the functional groups that you will be responsible for in this course. There's a lot of them in here, and this goes far beyond the functional groups that are illustrated in Chapter 1. What we want to look at is sort of similarities. So these groups, these are all hydrocarbons. So they mainly have carbon-carbon bonds and carbon-hydrogen bonds. Here I have single bonds. Here I have double bonds. Here I have triple bonds. And then this is a benzene-like structure. which characterizes aromatic compounds. The next couple are similar in that they have a carbon atom attached to an electronegative atom. So here, if it's a halogen, it's called an alkyl halide. Here, if it's an OH, it's called an alcohol. If I have carbon, oxygen, carbon, it's called an ether. If it's attached to nitrogen, it's called an amine. These next two groups are carbonyl containing molecules. This is a carbonyl group. So when I have carbon attached to one side and hydrogen attached to the other, it's an aldehyde. If I have carbon and then another carbon attached to the carbonyl carbon, it's going to be a ketone. So you can actually sort of look at these structures and look for commonalities and look for ways to remember them without memorization. If you kind of chunk them into different groups based on the characteristic atoms in the functional group, then it'll make it easier to remember all these different ones. This is a carboxylic acid. It's got this this is also written as CO2H, as COOH. These guys are called carboxylic acid derivatives because this central piece, if I look at this OCO, right, that's in all of these pieces. So it's a derivative of a carboxylic acid. So this is replacing the oxygen. This is replacing the oxygen. This is replacing the oxygen. But it all starts from here. It's a derivative of that carboxylic acid. This is an anhydride when this other piece is another carboxylic acid. When this is just another carbon, it's called an ester. When it's a nitrogen, it's called an amide. And notice these amides could have hydrogens, one hydrogen and another carbon group, or it could have two carbon-based groups attached to it. So those are all carboxylic acid derivatives. This is that base group here, the carboxylic acid. And then these guys are sulfur containing. So I have a thiol, which is sort of the sulfur counterpart to an alcohol, which is an OH. So this is an SH. I have this sulfur-sulfur, which is a disulfide. And here where I just have the carbon, sulfur, carbon, this is like an ether equivalent, right? Ether is carbon, oxygen, carbon. So when I replace the oxygen with the sulfur, this is the thiol of a, the sulfur counterpart to an alcohol, because an alcohol is OH. Here I have SH. So again, I have this huge chart, but I've sort of chunked them into groups that make a little bit more sense. And if you can remember them based on how they relate to one another, and you look for patterns in this course, it makes it a lot easier to understand rather than memorize. So these next slides just go over what I just sort of indicated on the chart themselves. The first four families are hydrocarbons. I only have carbon and hydrogen in something that is a hydrocarbon. Alkanes have only single bonds and really have no other functional group. we're going to note that we're going to use the term alkyl a lot. An alkyl group is something that is from an alkane. And we'll talk about that later. Alkenes, notice the ending, E-N-E, instead of A-N-E, have carbon-carbon double bonds. Alkynes, notice Y-N-E-S. They have that carbon-carbon triple bond. These are sp3 hybridized, these are sp2 hybridized, these are sp hybridized. Then I have aromatic compounds, which I have this 6-membered ring of carbon atoms with alternating double bonds. So I have this feature in the aromatic compounds that we're actually going to be talking about. This is just carbons that I haven't really drawn in, like on the slide previous to this. The next 4, remember, functional groups have only single bonds, and then I have a carbon that's bonded to an electronegative atom. So halides have carbon halogen. This is carbon fluorine, carbon bromine, carbon chlorine, carbon iodine. Alcohols always have a carbon bonded to an OH, right? Ethers have carbon O carbon. Amines are going to have a carbon with a nitrogen of some sort bonded to it. The next 6 families are going to have this carbon-oxygen double bond. And here they've grouped all of the carboxylic acids, their derivatives, and as well as aldehydes and ketones into this. I sort of break them into the aldehydes and ketones, and then the carboxylic acids and esters. But what they all have in common is this carbonyl group, which is that carbon double bond O. The next 3 families have carbonyls that contain, they have functional groups that contain sulfur. So the thioalcohol, the sulfide, which is sort of like an ether, but instead of the oxygen, I have a sulfur, and then the disulfides, which has that SS in there. These disulfides actually play an important role in protein functions. So it should be noted that the importance of a functional group cannot be overstated. The functional group that is present in a specific molecule determines all of these properties listed. It determines the bonding and the shape, the type and the strength of intermolecular forces that are present. That in turn is going to determine the physical properties of that molecule. Organic compounds are named nomenclature according to the type of functional group that's present. And most importantly, the chemical reactivity of a molecule is going to be decidedly determined by what chemical or what organic functional groups are present. So let's go over some terms. Most organic carbons, or most organic compounds, have carbon-carbon and carbon-hydrogen bonds. You're not going to find many that don't. But in addition to that, they have these other structural features that we're going to talk about. One structural feature can be a heteroatom, and that's atom other than carbon or hydrogen. So heteroatoms are oxygens, sulfurs, nitrogens, phosphorus, those atoms that are not carbon. I can also have pi bonds. Remember, I could have a carbon with a double bond or a carbon that has a double bond to oxygen, and that is going to have those pi bonds. I have one sigma bond, and then the second is that pi bond. these structural features that we're talking about are what distinguish one organic molecule from another. So just like with hybridization, right? This is sp2. If I have an alkane which is all singly bonded, that would be sp3 carbons, right? This is going to determine a molecule's geometry, the physical properties, and the reactivity, and all those things are determined by what functional groups are present. Now, heteroatoms and pi bonds actually are very reactive. Heteroatoms generally have lone pair, and they can help create electron deficient sites on carbon. If I have a carbon atom bonded to an oxygen, like in an alcohol, this bond is polar, and my electron density is pulled away from the carbon, becoming partially positive, where the oxygen becomes partially negative. So this is an electron deficient site on carbon. That is part of the reactivity of these alcohols. Pi bonds are easily broken. Remember, all I have to do is twist it in order to break it. That is a site of electron density, right? So this makes the molecule a base, which is an electron donor, or a nucleophile, which is something that is electron rich and can attack electron poor carbon atoms. So again, this polar bond here is making this carbon electron deficient because of the electronegativity difference between oxygen and carbon. This pi bond is making this a base and a nucleophile. So those are reactivity centers. Those are centers of reactivity. Don't think that the carbon-carbon and the carbon-hydrogen bonds are unimportant. They're really critical in forming the carbon backbone of the skeleton to the functional group of the overall molecule. So let's look at the difference between a couple of functional groups. Let's look at ethane. This has only carbon-carbon and carbon-hydrogen bonds. It really has no functional group per se. No polar bonds. This is totally non-polar. There's no lone pairs. There's no pi bonds. The only thing I have here is I have carbon-carbon bonds and carbon-hydrogen bonds. When I look at ethanol, this has an OH group, right? This is called a hydroxy group. I have two lone pairs on the oxygen. Because the oxygen is electronegative, that carbon-oxygen bond is a polar bond. The oxygen-hydrogen bond, these two types of bonds are polar bonds. They can react with a variety of reagents. The hydroxy group makes the properties of ethanol much different from the properties of ethane. When I look at carbons that contain the C double bond O group, this is called a carbonyl group. This polar carbon-oxygen bond, right, that's a polar carbon-oxygen bond, that's also pulling electron density. My electron density is pulling towards the the oxygen, which makes that partial negative and this part partial positive. That means the carbon is an electrophile, which basically just means it's electron deficient. It wants electrons, so it can react with nucleophiles. The lone pairs on this, right? So I have a lone pair here and here. That can allow it to react as a nucleophile and a base because of that lone pair. This, remember, is an area of electron density, which is what a lone pair would be. I also have a pi bond, right? That pi bond can also be more easily broken than a carbon-oxygen sigma bond. So this reactive features, I have lone pairs, easily broken pi bond, electron deficient, which means this is electrophilic, electro-loving carbon. It's very reactive. It has a permanent dipole. So when it interacts with another compound that has a carbonyl, I have dipole-dipole interactions. So there's a lot of chemistry just based on these simple functional groups. So based on what we know, which of the following is an aldehyde? Well, an aldehyde is something that contains a carbonyl. And on this side, I have a carbon group, and on the other side, I have a hydrogen. So this is carbon, carbonyl, carbon. This would be a ketone. This is carbon, carbonyl, hydrogen. This is the aldehyde, which is the answer. This is carbon, oxygen, carbon. This is an ether. And here I have carbon, carbonyl, OH. This is my carboxylic acid. So you need to be able to recognize these functional groups when you see them in compounds. Right, which of the following is an ester? Let's look. Carbon, carbonyl, carbon, that's ketone. Carbon, carbonyl, nitrogen, that's amide. Oxygen, carbonyl, carbon, where this oxygen is attached to another carbon. Remember, COOOH is a carboxylic acid. C double bond OOC, this is the carboxylic acid. This is a carboxylic ester. So this is the answer. Here, double bond with the OH, this is a carboxylic acid. So this is the ester right here. So again, you need to be able to look at these and you need to be able to recognize them. Which of the following is an amide? Carbon, double bond O carbonyl, carbon, ketone. Carbon, carbonyl, nitrogen. This is an amide. So that's an answer. Carbon, carbonyl, nitrogen. This is also an amide, right? So this is also an answer. Does not matter which order my carbon is. If I just take this one and flip it over by 100 degrees like a pancake, what I'm going to get is CH3, carbonyl, NH2. These are equivalent. We have to get used to recognizing equivalencies in structures. I can write them any which way, forwards, upside down, backwards, left to right, right to left. And unless I change connectivity, I'm not changing the overall structure. So we're going to learn in chapter 3 and after that I have to be really good at looking at structures and sort of figuring out if they're the same or they're different, and I need to look at atom connectivity in order to do that. Here I have carbon, carbonyl, OH. That's a carboxylic acid. Now, these functional groups control the physical properties, including boiling point, right? The boiling point of a compound is the temperature at which liquid molecules are converted into a gas. In boiling, right? As I transition from the liquid phase to the gas phase, I need to add energy, and that energy is needed to overcome the attractive forces, right? These are my intermolecular forces that we've talked about before: dipole, hydrogen bonding, and London dispersion forces. Remember, the stronger the intermolecular force, the higher the boiling points. So if I compare apples to apples and I look at the compounds with the same molecular weight, these are my London dispersion forces. Sometimes they're just referred to as van der Waals, even though we consider from the other lecture series that all of these are considered van der Waal. But when you just see this is van der Waals force, usually it's referring to London dispersion. This is dipole-dipole, right? These are polar compounds. These are nonpolar compounds. And these are compounds that have an oxygen or a nitrogen or a fluorine attached to a hydrogen. I have to be able to hydrogen bond, I have to have a hydrogen attached to a very electronegative, which is oxygen, nitrogen, or fluorine. This is the strongest force. This is the weakest force. This is the mid-range. So if I look at the examples below, if I can characterize the type of intermolecular forces that are present by looking at the structure, I can figure out which one's going to boil at a higher temperature. So this is pentane, right? This is an alkane. It's only got carbon-carbon bonds and carbon-hydrogen bonds. It's totally non-polar. So the type of force that this is going to have is just London dispersion forces. This is how you write an aldehyde, right? So this is actually the same thing. This is a polar bond. It has a permanent dipole. So this is going to have dipole-dipole interactions. This has got the oxygen attached to the hydrogen. So this can hydrogen bond. Remember, this is strongest. This is weakest. And you can tell as I go from London dispersion to dipole-dipole to hydrogen bonding, I have an increase in boiling point because I have an increase in the strength of the intermolecular force that's dominantly present. And that's going to require more energy to phase change, to pull apart those molecules to go from the liquid to the gaseous phase. Remember, if I have similar functional groups present, I'm going to look at surface area. The larger the surface area, the higher the boiling point. And the more polarizable something is, the higher the boiling point. This is generally when I look at London dispersion forces. If I have mixed, very long molecules that have a lot of hydrocarbon pieces, and then I have a little bit of a polar group, maybe an alcohol or an aldehyde, I have to, sort of take that by a case-by-case assessment. So these examples illustrate those 2 points. If I have acetone, which just has a 1 carbon, right? I have a very small nonpolar piece here, right? Here, I have a larger polar, nonpolar piece. So if they both have a carbonyl. So this is in common, right? So now, which is going to have a stronger intermolecular force? I have to look at the surface area. So if I look at this guy, I have 2 carbons, right? This is longer and skinnier, or longer than this one with just the CH3. The CH3, CH2 has an additional carbon, right? So now I have more surface area. So I'm increasing my London dispersion forces. My dipole-dipole is going to be the same in both molecules, right? But I have a higher London dispersion force because I have more carbons. This has a larger surface area. It has a higher boiling point than that one. And that's a pretty significant change. Adding those two carbons brings it from a boiling point of 56 to a boiling point of 102. Here's another example. This is a halogen, right? But it's iodine. So it's a larger, more polarizable atom. Fluorine is very small, right? It's only in row 2. Iodine's got a lot more shells, right? You can tell there's a ton of more electron cloud here, which means I increase London dispersion forces. This is more electronegative. This is actually more electronegative than iodine. But notice this is a higher boiling point. So this is an increase in dipole. But because this is so much more polarizable, this actually has the higher boiling point. So again, this is a case-by-case basis. If I asked you to put these in order of increasing boiling point, you need to say this is more electronegative, so the dipole is increased, but this is a much larger atom, so it's much more polarizable. That increases the London dispersion force. Since this is the same and this is the same, the CH3 are the same in both molecules, I have to sort of guess what's going to have a larger effect. If you said that fluoromethane has an increased boiling point because it has an increased dipole, you would be partially right? You have to think about these things. You have to make an argument about why you think one would be different than the other. You have to analyze the compounds, look at the similarities and look at the differences, and then assess what effect those differences and those similarities are going to have on the physical properties and the reactivity. So which has a higher boiling point? This is completely nonpolar. It only has London dispersion forces. This has a polar carbon-oxygen bond. So this is polar, and it has dipole-dipole, right? So this is going to be higher because it has the stronger intermolecular force. So again, you need to assess this. Which has the higher boiling point here? Well, this is hydrogen bonding. This is polar, right? I have a carbon-oxygen polar bond here. I have a carbon-oxygen polar bond there. This is going to be a polar molecule, so it'll have dipole-dipole. When I compare this, hydrogen bonding is a much stronger intermolecular force. So this compound is going to have the higher boiling points. Now, let's look at the influence of functional groups on reactivity. Functional groups are those groups of atoms that create reactive sites in the molecule. Things that are electron rich react with things that are electron poor. All functional groups contain some heteroatom, a pi bond, or both. Those features, as we discussed, are going to create something that's electron deficient, which is called electrophilic. It doesn't have electrons, it's electron loving. or something that's electron rich, this is nucleophile loving. So this is very negative, right? It wants a positive, which is a nucleophile. Molecules react at these sites. So I have to look at the structures, figure out where I have electron rich sites, where I have electron poor sites, where I have my heteroatoms, my pi bonds, or both, and I have to figure out what happens. Electron rich always goes to electron poor when we talk about this. So here, right, I have an electronegative chlorine. This is a polar bond. So this is a polar carbon-chlorine bond. This is an electronegative oxygen, right? This is a polar carbon-oxygen bond and a polar hydrogen bond. Because electron density is being pulled in this direction, this carbon here and this carbon here are partially positive. Partial positive is electron poor, which is electrophilic, right? Here, I have these lone pairs. Well, lone pairs, right? This is electron density. My lone pair is electron rich, right? These are my negative charges, my partial negative charges, and my lone pair that can be nucleophilic. They want to get to react with something that's more positive. My pi bonds, right? I have the double bond, which remember I have a sigma and I have a pi. Here I have a sigma and then I have two pi bonds. These pi bonds are electron rich. They're nucleophilic sites. They, by those electrons in that pi bond are, right, those pi bonds are more easily broken. All I have to do is twist them a little bit to get that side-by-side overlap and break it. Those electrons that are there can then act as nucleophilic sites. So hopefully you guys have learned a little bit about functional groups that we're going to be talking about. And I gave you kind of a little overview and introduction to a lot of the topics that we're going to start looking at. So go through this. We've now finished chapter 1. This week, week 1 in the summer session is still going to be talking about chapter 3 in the next part. So this concludes chapter 1 and on to chapter 3. We skip chapter 2 for the moment and we go on to chapter 3. So everybody have a good evening. I'll see you soon.